Hello, this is UConn's MEO1 team. Our group members are Jake, Joe, and Mackenzie, working along with our faculty advisor, Professor Carbone, and in partnership with our sponsor, Acme Machinery. Acme Machinery is located in Norwalk, Connecticut. They produce high-quality foam spray proportioners that are both affordable and reliable. Acme Machinery is proud to say that their proportioners are made right here in America. They plan to expand into the foam spray market by developing a foam spray gun. Our project was to design a foam spray gun for their purposes. UConn's MEO1 team was tasked with designing a low-cost disposable foam spray gun, also known as the SFG. Spray foam is created by two chemicals, isocyanate and resin, which need to be mixed in a specific ratio in order to produce a certain effect. Soft foam forms at a 3:7 mixing ratio, while solid foam forms at a 1:1 ratio. The original design of the sponsor's SFG could not mix the two chemicals together to create foam. This led to our main requirement for this project, to mix the two chemicals together for the desired 1:1 ratio. We researched and designed a way to both achieve proper mixing and to enhance the spray atomization of the foam spray gun. The other requirements for the SFG were to be able to handle the operating pressures from 120 psi to 1400 psi. The other goals were for it to be built under $100, utilize an air purge, and produce a spray pattern similar to that of the Graco Fusion spray gun. To develop a low-cost SFG that can achieve proper mixing and spray atomization, we designed a static mixing chamber. This impedes the flow of the chemicals, causing turbulence in mixing to occur. As recommended by our faculty advisor, we added an air assist atomizer that would provide a fine particle spray while ensuring simplicity in our design. We designed our SFG to be modular. The internal components can easily be changed out. We also made the helix disposable, and the nozzle can also be changed out to different types for testing purposes. The mixing chamber design for the SFG comprises of the following components: an O-ring, a mixing chamber, two air fittings, a helix, a nozzle, and a cap. To enhance the spray atomization of the air blast shell, we determined the diameter of it by using the solder mean diameter SMD equation to capture how the air and chemicals were interacting. The SMD is a ratio between the volume and surface area of the droplets. We use the SMD to determine what the mass flow rate of air should be to achieve a SMD of 400 microns. Then we utilize the choked flow equation to calculate the area, this giving us a diameter of 1/8 of an inch. To optimize our design of the mixing chamber, we performed two simulations, one to determine the factor of safety and the other for the minimum length of the mixing chamber to achieve a 1:1 ratio. At the max operating pressure of the SFG, the setup of the simulation has 3 loadings and fixed support. The stress analysis simulation of the mixing chamber shows that the max stress occurs from the longitudinal stress at 12,150 psi. Since the yield strength of aluminum 6061 is 35,000 psi, the factor of safety is 2.88. To determine the proper mixing, we utilize the transport concentrated species physics coupled with the Fick's law diffusion model. We also modeled it as a turbulent flow using the K-omega model. Some of the assumptions were made that it was a fully developed flow, the average mixture density, and diffusion coefficients. The systems being modeled is the internal flow of the system, where there are 2 inlets and 1 outlet. Simulating the mass concentration across the length of the mixing chamber as a parameter shows that their outflow reaches 0.5, or that there was a 1:1 mixing ratio when the overall length of the mixing chamber is 3.4 inches. To validate our results from the simulation, we tested with no air assistance, a fan nozzle, and metal helix. In the video on the left, the two chemicals are mixed and become foam within a few seconds of being on the ground. This shows that our design was a success and performed how any SFG should. The pictures in the center and on the right of the screen are the aftermath of the SFG spraying. We expected this from the test, and the others shown are to test the performance of our design. We later tested the existing air purge on the SFG. An air purge uses compressed air to clean the SFG after spraying to avoid any clogging, and that's shown in these 2 photos. The next test is with air assistance, a fan nozzle, and metal helix. This image on the left is the gun with the air hoses attached, whereas in the previous test shown, there was no air assistance. This test was performed at 800 psi and 1200 psi to view the spray and the foam developed between the pressures. A typical foam spray gun uses a full cone spray pattern, therefore the performance with the fan nozzle is irrelevant in this test. However, we can conclude that the gun can perform at high pressures. One of the requirements was to build the foam gun for less than $100. We redesigned the front of the original foam gun, the mixing chamber, and the nozzle, so that the total cost for our design is $93.70. This cost analysis is only for what is circled in red. It does not include the original handle section of the gun, so we plan to redesign it by using plastic material instead of metal. With this redesign and that higher demand, resulting in lower manufacturing costs, we believe that we could manufacture the foam gun for less than $100. The ME01 team came up with a solution that allows the gun to achieve a 1-to-1 mixing ratio and enhanced spray atomization while maintaining a competitive build price of less than $100. Our future design will reduce the cost to $86.73 by utilizing plastic components. Thanks for listening to ME01's design presentation of a low-cost disposable foam spray gun.